All right, thank you very much. So this is going to be an extended version of my 15-minute talk. Sorry. So the idea is to use homological mirror symmetry to answer questions about symplectic topology, which you can ask and answer without any A-infinity categories. So I'm going to start by giving some background about symplectic mapping class groups following Paul Seidel's lectures on four-dimensional Dehn twists. So a symplectic manifold is an even-dimensional manifold equipped with a closed two-form whose top power is a volume form. It's everywhere non-vanishing. So an example, but not the only example, is where X is a complex manifold omega is a Kähler form. And the object we're going to be studying today is the topological group of symplectomorphisms from X to itself. Diffeomorphisms from X to itself that respect the symplectic form. So in this case, where X is a complex manifold, of course you could have a complex automorphism that respects the Kähler form, but this group is much bigger and infinite dimensional. So if X is a surface, omega is going to be an area form then any symplectomorphism is an orientation-preserving diffeomorphism, and in fact this is inclusion is a homotopy equivalence, so we can just study this topological object and forget about the symplectic geometry in the problem. But in higher dimensions, that is not the case, as we'll see. For example,
is it trivial or a well-known fact? I did the result, but is it trivial? How trivial is it?
This is Moses' theorem. I mean, it's not. Once you know Moses' theorem, it's not extremely deep.
It's not extremely
deep. It's not extremely difficult.
It's not extremely
deep. So we can equip R4 with a standard symplectic form, and the compactly supported symplectomorphism group is contractible. This was proved by Gromov. The analogous question about the compactly supported diffeomorphism group, it's not known what the compactly supported diffeomorphism group of R4 is. So this is something symplectic. Gromov also proved that if you take CP2 with its Kähler form, Fubini-Studi Kähler form, it's homotopy equivalent to PU3, which is the things that act linearly on CP2, preserving the Kähler form. And if you have CP1 cross CP1 with equal area forms on the two factors, then you get SO3 cross SO3 semi-direct product Z mod 2. So you have rotating this one, semi-direct product, the thing that swaps both of them. On the other hand, if we allow the area of the second factor to vary, then the topology of this group varies with lambda. Well, somewhat wildly. The rational cohomology jumps each time lambda crosses an integer, for example. And this was worked out by Gromov, McDuff, Abreu, and Anjush. So the technique with all of these, to prove these results, is to look at some foliation on our space by holomorphic planes or spheres. And then if you've got some symplectomorphism phi that takes this foliation to a foliation by the push forward complex structure, and then you can deform the push forward complex structure back to the original one through almost complex structures to get an actual holomorphic automorphism. That's the rough idea. But in the case where we don't have a nice foliation by J holomorphic surfaces, we don't have that technique. We need something different. So when we don't have this nice technique using foliations, the first thing we can try to study is the symplectic mapping class group. So that's the group of isotopy classes of symplectomorphisms from X to itself. No, I'm going to talk about X being compact mainly. So the topology on this group, of course, matters for this pi naught, but if X has no H1 with coefficients in R, then we can just take the smooth topology on this, and the C infinity topology, sorry. So one source of interesting classes in symplectic mapping class group is where we have a family of projective varieties, family of smooth parameterized by some base B. And when we have this situation, we can equip each fiber of our family with a symplectic form, in fact a Kähler form, which is the Fubini-Studi form on projective space restricted to our subvariety. And we have a monodromy map from pi1 of the base into this symplectic mapping class group of the fibers. So here's an example. We can look at a fiber, we can look at a family over the complex disk, which is not a family of smooth projective varieties because the central fiber x0 has a node, or an A1 singularity. But if we remove this central fiber, this fiber over 0, then everything else is smooth. Then we get this monodromy map, where of course the fundamental group of our base of our family is now Z. And this map sends the generator of the fundamental group to the Dehn twist in the vanishing cycle associated to this singularity. So what does this look like? Well, there's a picture in the one case of one-dimensional fibers, which is enlightening. It's traditionally drawn like this, even if it's maybe not completely accurate. But we have some fiber over B here, which is smooth, and we have some fiber over 0, which is not smooth. We have some vanishing cycle, which we call L. And the monodromy, as we go around the base, takes this K to sorry, it's not really that different of a color. Takes K to this tau L of K. The tau L is this Dehn twist. Right. And it acts on homology by this Picard-Lefschetz reflection. Takes A to A plus or minus, with a sign depending on the dimension, A dot L times L. Okay. In the four-dimensional case, this ends up sending it turns out that this formula gives an actual reflection in the usual sense we think of it. So if you square it, you get the identity on homology. So we give a name to the subgroup of symplectic mapping classes that act trivially on homology. We put a superscript 0, and this tau L squared lies in there. And it even lies in the kernel of the obvious map from the symplectic mapping class group to the smooth mapping class group, which we denote by putting a subscript triv here.
Is there a difference between taking a subgroup of pi 0 of symplectics that act trivial on homology versus start by taking symplectomorphism that act trivial on homology and then take pi 0 of that? Is it the same thing or not?
It's the same thing, yeah. I mean, the automorphisms of cohomology is a discrete, yeah.
No, never mind.
Okay. So there are interesting things we can find inside this symplectic mapping class group using monodromy and in particular Dehn twists. We can find copies of the braid group. Yep, that's, yes. Compactly supported symplectomorphisms where X is a non-compact symplectic manifold. So we can find copies of the braid group embedded inside the compactly supported symplectic mapping class group of certain non-compact symplectic manifolds. And if we look at the pure braid group sitting inside, that's going to embed into the compactly supported symplectic mapping class group of things that are actually smoothly trivial. So we can find this big thing inside that's, has nothing to do with any sort of smooth topology. It's purely a symplectic thing, because as far as the smooth mapping class group is concerned, it just doesn't see that the image of this map is.
Here X is something special.
Yes.
For example, in singularity.
Yes. X could be, for example, an AM singular, AM Milnor fiber.
Okay.
Elsa Keating. Similarly, for non-compact symplectic manifold X, you can find copies of the free group on two generators injecting into this same one that's smoothly trivial things. Okay, so you can find, big, interesting subgroups inside this group. And the way you prove this injectivity is not by looking at foliations like we had before. It's by looking at the action of this group on Floer homology, which is an invariant defined using J holomorphic curves. All right. In the latter case, you can take it to be certain Milnor fibers. You basically need two Lagrangian spheres that intersect sufficiently many times that their Dehn twists, really mix each other up. Sorry?
Transpose intersections?
Yes. Okay. So let me state the theorem. This is joint work with Ivan Smith.
You know if you could put a rigid type of group like SL3Z, property T group?
I have no idea. Sorry. Yeah. Elsa and Paul might be the ones to ask. Okay. So our result is that you can find a compact symplectic four-manifold such that the trivial part of the symplectic mapping class group, smoothly trivial part of the symplectic mapping class group, is infinitely generated.
Is it known that the group is countable or not? How infinite?
Countably infinitely generated, yes.
It's a countable group.
It's a countable group, it's not. Okay, good.
Okay. It's the free group on a countable set of generators. Sorry, no, it's infinitely, there's no presentation with finitely many generators. No. I'm going to tell you what it is explicitly. So yeah, in fact, I can describe X very explicitly and tell you explicitly what kind of omega we're going to look at on it. So let me do that now, and then we can get more precise results than just it's infinitely generated. Okay, so I'm going to describe X in a few steps. We're going to look at this family of, sorry?
And X is not a genus 2 surface cross S2.
Okay.
Simplify.
Sure, yeah. Thanks. Yes, so in my 15-minute talk, Paul also corrected my statement of this. Well, I'm getting there. So we're going to look at, was there a question?
Is that a trivial case that we're excluding now?
The genus to surface cross S2 should probably be easy to prove. Yes, it is actually true.
Okay. Right.
By affiliation method.
Okay. All right, well, this is a different example that uses different techniques.
Oh, actually, that wouldn't lie, sorry, sorry, for the genus 2 case, it would lie in SIP0x, but it wouldn't lie in
yeah, okay, yeah, it's not smoothly trivial, yeah.
It's not smoothly trivial because you use the fundamental.
Yeah. Okay. All right. So we're going to look at this one parameter family of hypersurfaces in CP3, parameterized by T. We have a group here. Z mod 4 to the fourth acts on CP3 by multiplying the homogeneous coordinates by powers of I. The diagonal action is trivial, so this quotient also acts. And now we're going to look at everything in this group where the sum of the four elements is 0 mod 4. Those are the ones that preserve this monomial. So this whole group acts on each, preserves the fibers in here. So we're going to look at the quotient by this group, take the quotient of each fiber. And you end up with the quotient thing having 6 A3 singularities. These are ones that look like C2 quotient by this Z mod 4 action locally. So we're going to resolve a family X prime over C. Now we note that if we multiply T by I, there's a natural way of making the T fiber isomorphic to the IT fiber. Basically, that comes from looking at the action of this group on the total space.
Maybe, but what do you mean by this bar?
It's you'll see. Basically, it's gone. If I have a bar, it means I'm including some singular fibers. Some of the fibers in this family are singular. When I remove the bar, it's going to mean it's a family of smooth fibers, which I can take monodromy for. Okay. So since we have this extra symmetry in our family, we actually get a family over the base B, which is C, but with a Z mod 4 orbifold point at 0. Or in other words, C mod Z mod 4. Because the origin is a fixed point of this action by multiplication by I.
I think in some disk around origins, you might have some similarities further out.
No, you don't. No. Yeah, I haven't removed the singular fibers yet, but there's only one conifold point. So there's exactly one singular fiber in this family, which is the fiber over 1. So when we remove that one, we get a family of smooth projective varieties over this base B, which is the complex plane with one orbifold point at the origin and one puncture at 1. All right. T equals 0 is the Fermat. Yeah, you could compactify this to a fiber at infinity. That would definitely not be smooth. Be the normal crossings thing. Well, it has an orbifold point.
Okay. And do you remove the puncture 1?
Yes.
Okay.
Okay. So we had these 6 A3 singularities in each fiber. When we resolve them, each one gives us 3 components of an exceptional divisor above each. So we get a total of 18 exceptional curves inside this H2 of our fiber. We have another divisor E19, which is the pullback of the hyperplane section. That also has a class in H2 of XB. And we're going to look at Kähler forms omega so that the cohomology class, this is a closed 2 form, so it defines a class in de Rham cohomology, is a combination of these, some linear combination of these 19 classes I've defined in H2. but our results are only going to apply in cases where these coefficients are rationally independent.
Rationally pairwise independent.
Beg your pardon?
Pairwise independent, you mean rationally
Linearly independent.
Linearly independent over Q. Okay.
to get the Taylor form.
For, I beg your pardon?
Sorry. How to get the Taylor form with that property? Is it obvious?
How do you mean?
So how to construct the Taylor form with that property?
In the Kähler cone, so the condition of a cohomology class being the cohomology class of a Kähler form is open.
Yeah.
So if you have any Kähler form that is a combination of these classes,
Okay.
then you have a ball around this lambda. So somewhere in there will be
Okay.
one with
Get
these
the
properties.
Taylor class.
Sorry?
Get the class.
How do you get the Kähler class?
How to
Uh,
get this Taylor class?
You need to,
Just embed it somewhere.
so we have, yeah, we can embed it in, so it's a little bit more general. Than what I originally said for monodromy. We can embed it, we can choose a bunch of ample divisors and use the ample line bundles and use them to embed this X into a product of projective spaces. And then we can take some combination of the Fubini-Studi forms on these guys with coefficients lambda I, say, and pull it back. Okay. Okay. Sorry, let me erase this. I'm sorry, I just want to connect with that diagram. So we can take some cover of B so that whose covering group is the kernel of this map to automorphisms of cohomology. So then pi1 of this cover is going to map to symplectic mapping classes which act trivially on cohomology. And in fact, the image of this map is going to be lie in this smoothly trivial part. This cover is going to be the upper half plane minus all the pre-images of this 1 that we punctured from B. And the monodromy around each puncture is going to be a squared Dehn twist. Its image in here is going to be the squared Dehn twist. And we know all of those are smoothly trivial. So in fact, this map lies in a smoothly trivial symplectic mapping class group. All right. So of course,
You choose the cover corresponding to the smooth 3, so the index smooth 1.
yes, corresponding to the map from here to automorphisms of cohomology. So of course, if we remove all the pre-images of 1, there are infinitely many. So the fundamental group of this B tilde is going to be a free group generated by loops going around each of these punctures that we remove. So that this is an infinitely generated free group, countably infinitely. Yep.
What's going on with the orbital point?
Well, the orbifold point is t equals 0. That's this Fermat guy, which has an extra symmetry. So, yeah, you're right. I should have put an orbifold fundamental group for both of these guys. So the generator, the loop going around that orbifold point once has order 4. Its image here has order 4.
Sorry, so what is the upper half plane? Is it covering of what?
C minus this minus 1, and with a Z-mod for orbifold point at 0.
But then why do you have to take, if it's a covering of this minus 1, why do you have to take out the pre-images of 1?
I mean, we took out 1 in there.
Yes, but in order to form the covering H, you already removed 1.
Wait. I'm not following. H. I mean H is not a.
The claim is that 1 is already removed from B. So when you say 1 in, I mean,
Is H tented at 1 or is it?
Oh, okay. Oh, okay. I see what you mean. I mean, there is a map from H to B.
And where is the map branched?
Yeah, what is wrap around? Does it wrap around 0 or 1?
It wraps around both. I believe it has.
Oh, so it has index 4 at the Z4
Yeah.
order point.
Yes,
2 at
and
the
order
point 1.
index 2 here.
Okay,
Yes.
okay, now we got
Yes.
it. Okay, so 1 minus a quarter minus a half is still positive. Maybe I shouldn't have done that. No, I'm sorry. What is it?
So what's 5-1 orbifold?
It's okay.
Anyway, so you can probably just say generators for 5-1 orbifold of B comma E, right?
Sure.
So there's
I mean, there are
generators, 1 or 4 and 1
pi 1 of this thing. Yeah, there's one generator going around here, one generator going around here. This one has order 4. This one has infinite order.
and you have the subgroup of finite index and
It has infinite index. The covering group is covering group is some specific matrix.
Plus Stanford?
Beg your pardon?
Is it plus Stanford?
yeah, so this is the guys in PSL2R where C is even, and I think it's -1 and √2. You take this one together with this one. Okay.
Sorry to interrupt. Can you maybe describe some of those generators of continuity? What is this in group in terms of words and their original pseudo generators, or is it complicated?
Words in the original two generators.
Remaining generators, this one inside this generators.
They are all going to be conjugate to the one going around this guy twice.
I see.
Conjugate that guy by whatever you want. Okay. All right, so let me state the theorem. So we have this. These maps here. And now finally, we're going to have some categories appearing, some invariants of our symplectic manifold that we're going to use to study this group action. The Fukaya category is an invariant of our symplectic manifold. It's the invariant is a category. So it's a symplectic invariant, so we have a map from symplectomorphisms to autoequivalences of this category. And it turns out, in this case, the isotopic symplectomorphisms define the same autoequivalence of our category. So in fact, we have a map from pi0 of this guy to autoequivalences. I got these the wrong way around, didn't I? Sorry. Okay. And the result is that if we look at a certain subgroup called Calabi-Yau autoequivalences, then this composition is an isomorphism, and this composition is also an isomorphism. So
it's much more than just realizing the group inside.
that's right. Yeah. We I beg your pardon?
So we have to apply the zero.
Yes, there is. So I didn't explain what these ones correspond to. Upper index 0 means autoequivalences which act trivially on an invariant called Hochschild homology of the category.
Are there non-Calabi automorphisms?
Yes.
Like?
I mean, if you took, sorry?
You're saying the other thing is this other thing that can, without the Calabi?
Yes, this is yes. I mean, if you have just an automorphism of your category, sorry, maybe it's easiest if I say something on bounded derived category of coherent sheaf side. If you had some automorphism of the category that acted non-trivially on the canonical bundle.
But does this one happen?
Yes, the things that are mirror to those. It's just that anything coming from a symplectomorphism is always going to be Calabi.
Not every K3 has these automorphisms. Which
Sure. Okay. Yeah, I would.
Does it because it's mirrored to this one here? You can rotate one of the coordinates.
Sure. Yeah, I can't think off the top of my head. Sorry. So to say quickly, there is a natural way of finding isomorphisms between Hom from K to L and Hom 2 minus, in degree 2 minus this degree from L to K, dual, in the Fukaya category. And this subgroup is the subgroup of autoequivalences that respect that all of these isomorphisms. Okay, so it respects an extra little bit of structure. So in particular, since this is an isomorphism, this guy maps surjectively onto this one, which is F infinity. So this guy is infinitely generated. So that's the result I stated before. More precisely, the symplectomorphisms that act trivially on cohomology are isomorphic to this infinitely generated free group semi-direct product some group G. And the symplectic mapping class group is pi1 of this B semi-direct product, the same group G. I mean, you.
But you have this group. You've got these generators that you started out with.
Yes.
This construction. Then you onto at the end.
Yes.
So you actually identify generators of the other group and realize them.
Of which group? Of this one?
Would you actually be able to?
Yeah. I mean, Right. I mean, this one here, this generator is going to correspond to a Dehn twist.
Right. So the fact that you get
And
all
this-
these polymorphisms of the Fukaya category,
Yes.
I'm just asking if you prove it by identifying generators separately and then arranging that you get them, or not.
Yeah, I mean, in some sense, sure, but it's a little bit, well, I mean, it's a little bit more complicated than that.
Maybe that explains.
Okay. I can tell you part of it. For this guy here, you characterize what the image is here. You say for any object of this category that is spherical, there's an associated squared spherical twist, and you prove that you hit all of the spherical twists in here. And then the rest, there's a bit more to get this guy, but not that much more. Okay. All right, so So how do we prove this? Well, we need to get some handle on this autoequivalence group of this category, Fukaya category. So homological mirror symmetry tells us that this should be equivalent to this bounded derived category of coherent sheaves of some mirror variety, which in this case is another K3 variety just like X is. So we have to prove homological mirror symmetry in order to apply it, and we do that in this case. And the real heavy lifting to prove this theorem is done in a paper by Aaron Beyer and Tom Bridgeland, who basically compute what this autoequivalence group is, and they express it as pi1 of a certain space of stability conditions on the category. And they prove that in the case that X check has Picard rank 1. And now it turns out, okay, I erased it, that this condition that the cohomology class of the symplectic form has to be irrational is the thing that corresponds under homological mirror symmetry to the Picard rank of this mirror variety being equal to 1. There are a bunch of sort of, in the space of complex structures here, you have a bunch of divisors called Noether-Lefschetz loci on which the Picard rank is higher, and they correspond to Kähler classes where there's extra rational dependence between the coefficients in the Kähler form. So there's a conjecture due to Bridgeland that predates their proof of this theorem about what this guy should look like in other cases when the Picard rank is higher. And that plays just as nicely with homological mirror symmetry and suggests that this autoequivalence group of this category and Similarly, this symplectic mapping class group should really jump as the Kähler form picks up extra rational dependencies. Okay, but I should stop there.